Hi.
Hello? Can you hear me?
Yeah.
Yeah, how
How's
are
it
you?
going? Doing
Yes.
pretty good. So I
Yeah,
guess we can get started.
yeah,
Oh,
cool. Yeah,
yeah. Can you share the screen with the code bunk?
let me see. Oh, I just closed it.
Okay. So for this problem, suppose we're given an array of integers and a number k. What I'd like you to do is randomly move k elements to the right side of the array.
Randomly move the k elements to the right side of the array. Is there any example of?
Sure. We can do a simple one.
Yep.
Right. Suppose we have one, 2, 3, 4, 5. Right?
Yeah.
Suppose the random numbers chosen are 1 and 3. Right. Then when we move to the right side of the array, we end up with well, okay, 1 and 3 are at the end, and then the other numbers, I guess, would just be 2, 4, 5. Right? And it doesn't have to be in this order, as long as you pick two numbers and they end up on the right side, and then everything that was not chosen is on the left side.
Yeah, the number we pick are the input, or the input is just the k.
The array and k.
Array and k. I just randomly select the number, move to the back.
Right.
Okay, so 1 and 3 are randomly selected. So by the program. Am I correct?
Yes.
Okay. So is there any requirement for the space capacity?
I prefer constant space.
So I cannot. I cannot create additional array for it. Yeah, I think maybe I can talk about the brute force. For the brute force method, I pick one random number and I just move them to the end and in place, and pick the other one, move to the end in place. So the time complexity will be like k times n. That's the very simple vanilla approach I have in my mind. And let me see if I can get a better solution for it.
Oh, okay. So where is this n coming from?
M is the length of the array.
Yeah. Why is that in the cost?
Because each time I switch the, I'm sorry. I think I just switched the n, right? I don't need to move to. Yeah. So the order of the output array does not matter, right?
Yeah, that doesn't matter.
It doesn't matter. So I just switch to the end. Yeah, switch to the end. That should be good.
So what do you mean by switching?
Just switch the one I pick and the one in the last of the array, or maybe the last unpicked array. For example, if you you have 1 to 5, and 1 is the pick one, so I just switch 1 and 5.
Yep. Okay.
That 1 and 5.
Okay. What happens to the next number?
Next number is going to be switched. Yeah, there's some problem because if I switch 2, if I select 2, I need to go to 4. But it's very likely the number in the end is the one I already switched.
Yeah.
How about, let me see, how about like the partitioning?
So what can you switch with?
Can I use how about the partitioning method in the quick sort.
How can that help?
That can be done in linear complexity. But you want to select the k random number, so the random number is hard to choose. The random is not fixed.
Well, what's the problem with what you have now?
Right now is if I use the partitioning method, no matter what's normal or Horus method, I need to have like a criteria to move the number to the left and move the number to the right. So the criteria right now is the random select number. So right now I don't have because the number is randomly selected. Each time I check the criteria, the number is changing.
Yeah. So going back to your previous idea. So I think the first iteration, it makes sense.
Yeah.
What can we do in the second iteration to?
Second iteration is I need to have a point. The point should move from the 1 to 4.
Yeah.
And at this point, the 4 should be switched by the randomly selected number.
Okay.
Yeah, maybe I can try that.
Yep.
Okay. So it means the input, maybe write the function. It's a return with a vector and like a.
So it needs to not return anything.
Okay, you want to prefer in place?
Yeah, it has to be done in place.
Okay, great. Okay, so I have one pointer. So the number is, let's say J is equal to random. So that's one. Yeah. That's just copy anything.
Yep.
Copy anything. If that's a J, and when you have the other number called M, good. Yeah, should be the end. If the J is randomly selected, we swap. And we move in. The other problem.
Is this doing what you were describing earlier?
J randomly selector and swap J and A.
So why mod by the size of the input?
Sorry?
Why mod by the size of the input?
Because that's going to randomly selector.
Can anything go wrong based on what the result is?
It's going to be, yeah, of course, it will have a repeated J.
Yes.
How can we avoid the repeated J?
So how can we avoid that?
Yeah, I'm trying to think about it. Oh, yeah. Right. because since we have for the after first iteration and the number had moved to the end, so we should not multiply the end. We should be multiplied the minus the current step. Yeah, so because we will not consider the last one for the first iteration. For the second iteration, we will not consider the last two.
Yep.
So you only get the first minus I numbers. Okay. Yeah. You're right.
Yep. Yeah, I think that'll work. All right, cool. So now let's move on to another question.
Okay. No.
So this one was about finding k random elements if you already know them, all the numbers ahead of time. Now we'd like to develop an online version of the algorithm where suppose you don't know all the numbers ahead of time and they're streaming in. So I'd like you to write a class that has the ability to accept a new number and return k random numbers that it has already seen before, of the ones that it's seen before. So you might have something like a sequence like this, right? Accept 1. All right, let's say we've initialized it with k equals 2. Right? We might be able to do something like this, accept 2, right? And get random. So this would initially, it can only return 1, 2, right? Since we've only accepted 2 numbers. Now say we accept 3, right? After that, then get random. What can this be? All right, suppose we didn't call get random up till this point. We can get any of 1, 2, or 1, 3, or 2, 4. Sorry, 2, 3 that are equally likely.
As a combination. Okay.
Yeah.
So accept it just push the number like 1, 2, 3 into the array, and get random, it just randomly select the 2 after the 3 number, right?
Yeah, that's one way you could do it. However, the purpose of wanting to do this is so we don't want to use more memory for every number that comes in. Suppose we want to take statistics on a stream of values, but there are new numbers coming in very frequently.
Right.
And we don't want to use more and more memory over time.
Right.
I want to take just a random sample.
Right.
And then use that.
Yeah.
So we should aim for O of k memory usage.
Yeah, I think that's a good idea. So the class, I need to implement this kind of 2 public function. I think we can have a simple array as the class data member. Each time you accept the number, you just put the number into the array. That's how the accept function works. For the get random, you just simply we put the function we just implemented, and we return the first k, or maybe the last k numbers.
Well, that would be using more memory over time.
Oh, you mean okay. So,
yeah, what you described is O of n memory, where n is the number of, it's the number of calls to accept. But we want O of k to make it constant.
So so we can, each time we accept, once the array size larger than 2, we just render the function we just implement, and we pop up the first n minus k number, and then we'll keep the last k number.
Sorry, can you repeat that? What is pop out the first?
Just we pop up the first n minus k numbers. We keep the last k numbers.
I have to see an example of that.
So just like we push the 1, we push 2, and we push 3. Now we have 3 size equal to 3, right? Our k is equal to like 2, k equal to 2, and we run the function we just implemented. So we randomly select the 2 number and we move them to the back. So yeah, and the first number we don't need it. We'll just pop up the first number, or we'll just keep the last k number.
Oh, okay. So
run the function.
Okay, so you randomly delete how many?
Kind of.
I guess you delete 1 every time.
Yes.
I see.
Okay.
Great. So we'd like to guarantee that all the subsets of size k are equally likely.
Okay, you're right.
To be chosen by get random.
So my question is, once we push the 3 number, can we keep the 3 number before we call the get random function?
Can we keep?
Yeah, so like the above example, we push 3 numbers. Yeah, now we have 3, right?
Right.
Yeah, can we keep them? So
then you'd be using O of n memory if.
Yeah, all the memories.
Yeah.
So we cannot keep them, right?
Right. We should be. So yeah, it sounds like you only want to delete things on a call to get random. Right? So if that never happens, then I guess you keep accumulating more memory.
Right. So what if here we accept the 4? So the get random will create like something 1, 4 and others, right?
Yeah. So that's, I think, 6 different results.
Correct.
That are equally.
Yeah, 6 choose 2, 6. Okay, how can we do that by not deleting the number? So after we accept the 4, we cannot increase the memory to 4. We cannot.
Right. We need to be limiting the memory to k.
Memory to k.
Well, even if you did increase memory to 4, how would that help?
Now we have the vector of 4, and we run the function we just implemented, and we get the randomly select the 2 numbers. That's what I'm thinking.
Oh, okay. So in that, then get random and accept would both not delete anything.
Not to delete anything, right?
Yeah. Okay, that makes sense.
The memory will increase definitely. Each time you push the number, it will increase the memory.
Okay, so if we only keep k elements around, can we still get random subsets?
Let me think about it. For the number we accept, is there any relationship between these 2 numbers, or just totally independent?
They're completely independent.
Okay.
Just a stream.
Okay.
Yeah. You imagine, like, say something's measuring the temperature for every millisecond, or requests are coming to a server and we measure the latency.
Right.
So it's something that's happening very often, and
yes,
we just don't want to keep more memory over time. We want to just configure it to some k, and then know that only k memory will be used.
Yeah, can we do something like this? We prepare a array with a constant length, and once the number we push into the array has exceeds the length, we randomly select the number and pop them out. And each time we call to the get random, we just get a random number.
I see. So every time, in this case, as soon as you get 3, you randomly delete one of the previous numbers.
So each time, for example, let's pre-allocate like the size like 100. So once we accept more than 100 number, we randomly select the one of the number and we pop out.
Is that for k equals 100?
No, k equal to 2.
Oh, okay.
So I just select a number that's in the statistical view, it's much larger than k. And we randomly select the number from this pool, and each number should have approximately equal probability.
Okay, so if you have an array of size 100, then when someone calls get random, how do you find those numbers?
Yeah, we can use the render function, and we call them k times and get a number. We can just use the function we just implemented.
I see. So logic is, some size like 100 or something larger than k. And then whenever you accept a number and you have more than that, then you delete one at random. Okay.
Yeah, it's not the ideal way. It's not. Yeah, I think there should be a better way to do that.
So will that ensure our goal of equal probability for every subset?
It's not exactly equal. It's just like approximately equal. Okay. Yeah, I think. Yeah, I think it's not the best way. Let me think the other ways.
So what do you mean by approximately equal?
So the probability for each one is not equal. So someone maybe have a higher probability, the others may have a lower probability, and some might have been 0 because the one have been popped out, they must have a 0 probability.
Which numbers will have higher probability than others?
Obviously, when the one in the still stay in the pool should have a higher probability. Yeah. Anyway, I don't think this is a good approach.
One thing I should clarify is that get random is allowed to return the same thing over and over if you haven't gotten any new numbers.
Okay.
So it's okay that some numbers have been deleted and they'll never be seen again.
Okay. Oh, that's interesting. So there is like a value that storm the last return number of the get random. Is that what you mean?
Yeah. So can we? So if we go back to the idea of when you accept the k+1 number, can we delete something in the size k array? So the size k array we just maintain what's the currently random selected k subset, which is updated every time we accept a new number.
Okay. Okay. So you mean before we accept 3, we already, by the time we already call the random to randomly select the 2 numbers. Okay.
Well, we don't need any randomness for the first 2 since the k is 2. Then when we get the third number, we need to randomly, have the result be one of these three. And then when get random is called, then we just return that.
And we can delete the number from the get random. Sorry, delete the number we got from the get random from the array.
Well, get random will just return whatever is in the array. All the deleting and appending should happen in accept.
So when we call get random, we get the, for example, like 1, 2, and we accept the 3. Is that what you mean?
Yeah, that could happen.
Okay.
And then after accepting 3, get random can return any of these 3.
So for example, when we call the get random, we got like, for example, like 1 and 3, and we accept 4.
Yep.
And the total array become like 1, 3, and 4. And we get random from this 1, 3, and 4.
And so if you append to the array, then I think you're accumulating more memory over time. So are you suggesting to only delete things inside of get random?
Yes.
Then you still have the problem that if it never gets called, then you keep adding more memory.
Right.
Yeah, so all the work should be in accept.
Yes, in accept.
And
so each time we accept, I mean here, during the accept 4, we call the get random. And
right.
And we got the 2 number. We still keep the 2 number. And the next time we like accept 5. And during the accept 5, we call the get random. So we select the 2 number from the existing 3 number.
Oh, wait, so accept is calling get random to decide what to keep? Is that right?
Yes.
Okay. And that get random, is that the same as this function?
Yes.
Okay. Interesting idea. So is this going to guarantee that every subset has equal probability of being chosen?
Looks like not, because the first number pop up, you're going to have a lowest probability.
Right. So this algorithm that you're using here prioritizes more recent numbers.
Yes.
So how can we correct that bias and make sure that every number is equally likely?
Can we tweak the random selection process?
What tweaks do we need?
Maybe we reduce the probability for the latest number and increase the
yes.
Yes. How can we do that?
I think we're just about out of time.
Okay.
Okay, so I can go over the solution to this problem. The first problem, your solution is the optimal one. So we don't have to discuss that. For this one, I think it takes a little bit more thinking to ensure that the array we're maintaining has the correct contents with equal probability at all times.
Yes.
All right. So I'm going to write some pseudocode for accept. All right, so let's take care of the easy case first. If array that size less than k,
Right.
then we just push to the end, right?
Yes.
Okay. Now the tricky part is when we already have k elements, then we need to figure out how to delete something and replace it. Right? So let's think about what the possibilities are. Before we have 1, 2, right? Then when we accept 3, we have one of these, which are equally likely.
Right.
So a naive solution here would just be to have a 1/3 chance of keeping this. Sorry, a 2. So let's think. We already have an array of 1 and 2 in it.
Right.
Now the new number is 3, right? And we know that out of the possible results, 2 of the 3 contain the most recent number, right?
Yes.
So we could say with a 2/3 chance, delete one of the old numbers, with a 1/3 chance to ignore 3, right?
Okay.
So we're gonna say 2/3 probability, keep 3, replace 1 or 2.
Right.
And that's 50% chance of each of these, right? And then 1/3 probability would be to just ignore 3, right?
Right.
So that means each of these choices are equally likely. But this isn't the full general logic yet. Let's also think what happens when we accept 4 after that. And now what we have 6 possible results.
Right.
We have so every one of these pairs. 4. So there's a 1/6 chance of each of these, right? And when we accept 4, if we look at the possible results, we see that how many of them contain 4? Half of them, right?
Yes.
So where is that coming from? Keep 4, replace random existing previous number. 1/2 probability. Ignore 4, right? So if we ignore 4, then we're just keeping whatever was from before, right? When we accepted 3.
Yes.
And that's exactly 2, 1, 2, 1, 3, and 2, 3, right? So that's the 50% chance of that don't have the 4, right? And with this half probability, we end up with either 1, 4, 2, 4, or 3, 4, right? And it doesn't have to be in this order. Right? So how can we? Right. So you see that the probability was 2/3 previously, but now it's 1/2, right? So what changed here? Maybe it'll be clear once we do the accept 5 example, and now it'll be clear what happens, right? So let's think of it. Of all these sets here, how many of them will contain 5? The answer is 2/5 of them will have 5. Since we're selecting 2 random elements out of 5 total.
Right.
So 2/5. So let's put it this way: k out of n
And yes.
subsets will contain the new number, right? That's any given number.
Yes.
Right. So the probability will be like this, right? With probability k of n. So k was 2 here, right? N is 3, right? Keep new number, replace random previous number,
Right.
With probability, 1 minus k n. Ignore new number. So the simplest way to do this is to actually just generate a random integer from 0 to n minus 1. if that's a valid array index, then just put the number at that index. And if it's larger than the array size or equal, then just don't do anything. But well, so yeah, that's the solution to this problem. I have a code written in Java, which we can take a look at here. So it's fairly short, right?
Yeah.
Here's the solution in Java. So we keep track of a current size. Actually, that's the input size. That's K. We keep track of N as the number of elements we've accepted so far. And then we keep track of the current array. Constructor, which just initializes the elements. And we get a new number. We increment the number that the count that we've seen so far. And then we take care of the case that if we're in the first K elements, we just append it. With the remaining elements, we just randomly choose a number from 0 up to N.
Yeah.
N minus 1, that is, since we're not including N itself. And then if that's within the array bounds, we just replace the old number with that new number at that index. And then get random or get current will just be return whatever is the current array.
Yes. Yeah. I totally not thinking about the probability. Yes. I should go into that direction. Yeah.
Okay. Yeah. So I think a thought process that would really help for this question is to just look at what the expected outputs are, right? And so how I got the logic from just seeing that there are these possible outputs and what percentage of them have the new number, right?
Yeah.
And when we looked at that, it was clear that whatever percentage has a new number, that's the probability that we keep this and replace an old number. And 1 minus that is a probability that we just ignore the new number, right?
Right.
So if you're stuck in any way, it really helps to just look at the expected output.
Yes.
And then compare that to what it was before, right? And then see what changes are needed to make that expected output.
Yeah, you are totally right. Yeah. I think I just spent like 99% of energy thinking of how kind of a data structure can be used, these kind of things. Yeah, I didn't look into this kind of numbers, mathematical behind this. Yeah, I totally went into the wrong way.
Yep. Right.
Yeah, after you explaining this, I think it's, anyway.
Yeah. So that's just a general technique that can help you get unstuck on any problem. Right?
Yeah.
You can just look at an example, see what it is that you expect the output to be, and then work backwards from there to see what the logic was. Right? Yeah, and you see here, the logic for what to do in exception. It all came from just looking at the output, seeing that there's n possible numbers. Right? We're choosing k of them.
Yeah.
So k out of n of those subsets will contain the new number we added. Right?
Yes.
All right. So another thing that would help is as you propose ideas, it would be good to write some pseudocode to keep track of what you have so far. So you see what I wrote on line 33 to 36.
Yes.
That just it helps keep track of what you've discovered so far. Right? So here we keep track that we've already solved the problem for the first k numbers, right? And now we know that we need to solve for subsequent numbers only, right? So this is a great way to communicate your thought process.
Okay.
And also keep track of what you've solved so far, right? And that helps you, remember like which parts of the problem you don't need to solve in the future since you've already solved them, right?
Yes.
And it also helps when you're writing code, you just refer back to the pseudocode to see what the logic was, right? And you ensure that you don't forget any important aspects of the logic later.
Yeah.
So for the first question, I thought you had the optimal solution figured out pretty early. But then when you wrote the code, I saw that you were not doing the -I on line 84. So the random logic there would sometimes choose the same value multiple times as a result of that.
Yes. Yeah, so yeah, I think you're right. And so during the interview process, write down all this pseudocode and the logic.
Yep. Right.
Yeah.
So what I have in line 29 to 31 is pretty much the pseudocode for the rest of the function after this case.
Yeah, you are totally right. And during the practice, I never wrote the pseudocode, but I know from this mock interview, I know I need to do that.
Okay. So if you're not writing pseudocode, then there are probably occurrences where you figure out something important early, and then later you forget it.
Yeah, you are
this
totally
happens
right.
a lot with, say, edge cases.
Yes.
And also with any kind of algorithm that's complicated, has many parts, right? It's highly unlikely that you're going to remember all those parts perfectly. Right?
Yes.
The more difficult the algorithm is, the more likely that you'll forget some of it by the end. Right? So writing the pseudocode really helps keep track of things and make sure that if you figure out something very early, then 30 minutes later you won't forget it, right? Because it's written down. And that does happen that sometimes it takes 30 minutes to figure out a problem, and then only in the last 10 minutes of the interview do you start coding. And when you do get to that point, you want to have everything written down so that when you're coding, you can just look back here, right? See what the logic was, and then be able to code very quickly. Right?
Yeah, this explains everything in these lines. Yes. Right. Yeah. All right. Thank you so much. I think I learned quite a lot today. Yes.
Yeah. Oh, this is definitely not bad for a first mock interview. Yeah, a lot of people need more help to solve the first question.
Yeah. I guess I need more practice, and yes. Yeah, I definitely focus on different things, but afterwards, I think I should focus on the thing you was talking about.
Yep. All right. Well, I hope that was helpful for you. Yeah. Oh, it was nice talking to you today. Yeah, thanks for taking the time to do a mock interview.
Yeah, thank you. Thank you so much.